NASA detected a mysterious object speeding toward Earth. So on October 3rd, 3 Atlas will pass within 29 million km. A bright green comet has just appeared in our skies, turning telescopes and headlines toward 3I Atlas, the third ever interstellar visitor. And now we finally know exactly when it will make its stunning arrival. Official records say it was first spotted on July 1st, 2025, traveling a blazing 61 kilometers. Yet its emerald glow is unlike any comet ever seen, and no one can fully explain why. As it speeds toward its closest approach to Mars on October 3rd and the Sun on October 29th, scientists are scrambling to decipher the alien chemistry it carries. Because whatever answers lie inside 3 Atlas could reveal secrets older than our own solar system. Why did this mysterious wanderer turn green, and what might we miss as it vanishes into the void? The first hints of something extraordinary came not from professional observatories, but from the backyard telescopes of citizen astronomers. On the night of September 7th, 2025, as a total lunar eclipse painted the sky red, a flurry of images began to circulate online. In Austria, Michael Joerger captured a comet with a faint icy blue coma. Hours later, Gerald Raymond in Namibia posted a new frame, the same object but now wrapped in a vivid emerald glow. Across forums and social media, the reaction was immediate. Amateurs and professionals alike were stunned. No one could recall a comet changing color so suddenly, especially not to this shade of green. Time-stamped photos poured in from every continent. Each showed the same transformation, a neutral haze giving way to a green so intense it seemed artificial. The color shift didn't match any known cometary behavior. Normally, a green comet signals the presence of dicarbon C2 molecules fluorescing in sunlight. But the timing was off, the hue was wrong, and the brightness was far beyond what dicarbon alone could explain. Veteran comet chasers compared notes and checked their old data. Before the eclipse, the coma appeared ordinary, maybe a touch blue. By dawn, the new images showed a green halo stretching tens of thousands of kilometers from the nucleus, bright enough to be picked up even by modest equipment. In chat rooms and Slack channels, speculation ran wild. Was this a trick of the eclipse, a camera artifact, or had something inside the comet truly changed? Experienced observers double-checked their filters, calibrated their sensors, and reprocessed their data. The results held up. The green was real and it wasn't going away. Even as the moon left Earth's shadow, the comet's color stayed locked in place, defying quick explanations. Astronomers scrambled to schedule urgent spectroscopic follow-ups. But the amateur images had already set the tone. For the first time, the world was watching an interstellar visitor reveal a secret no one could decode. The question lingered in every new post and image. What could possibly cause a comet from another star to glow this way? And why now? On July 1st, 2025, the Atlas Survey Telescope at Rio Gerardo, Chile, flagged an object moving with unusual speed across the star-crowded sky. The system's software, tuned to spot fast movers, picked it out from a stream of ordinary detections. Initial checks suggested something rare. The object's arc didn't fit the closed looping paths of solar system comets or asteroids. Instead, its orbit was hyperbolic, open-ended, the mathematical signature of a visitor from beyond the sun's grasp. The Atlas team, spread across continents and time zones, dove into the data. Each new observation tightened the orbital solution. Calculations showed the object was traveling at nearly 61 km relative to the Sun, a velocity far too high for anything born in the Oort cloud or Kuiper belt. Even before the Minor Planet Center issued its circular, the Slack channels and group chats buzzed with the realization. This was only the third confirmed interstellar object ever seen after Oumuamua and Borisov. Confirmation came quickly. Follow-up images from other telescopes caught a faint coma and the beginnings of a tail, ruling out a bare asteroid. The Minor Planet Center assigned the designation 3 Atlas, third interstellar object discovered by the Asteroid Terrestrial Impact Last Alert System. Underneath the official announcement, the real excitement played out in the rapid-fire exchanges among the Atlas scientists. Published accounts describe a wave of AWE and disbelief as the hyperbolic trajectory held up under scrutiny. For some, it was the culmination of years spent refining detection algorithms and chasing elusive signals in crowded fields. The process was methodical but electric. Each new data point, each refinement to the orbital fit, reinforced what the amateur astronomers had only suspected. This was not a comet from our own backyard. Its speed and path could only be explained by an origin in another star system, perhaps billions of years and light years away. The professional confirmation set the stage for everything that followed. The urgent chemistry studies, the scramble for telescope time, and the sense that for a brief moment Earth was host to a messenger from the wider galaxy, spectroscopists across the globe turned their attention to 3 Atlas, hoping its green coma would reveal a familiar chemical signature. Instead, the data upended expectations. Every major telescope from Gemini in Chile to JWST in solar orbit delivered the same surprise. The classic fingerprints of dicarbon, the molecule that usually gives green comets their color, were missing. No trace of the swan bands, no sign of C2 even in the most sensitive spectra. The green persisted, but its source was invisible to the usual methods. What the instruments did find was a cocktail of gases never before seen in a comet, interstellar or otherwise. The JWST spectrum taken in August and September showed carbon dioxide lines dominating the infrared. The ratio of carbon dioxide to water was about 8:1, a reversal of the norm for solar system comets where water usually leads and carbon dioxide is a faint afterthought. This overwhelming presence of carbon dioxide hinted at a birthplace far colder than the edge of our own solar system. Perhaps beyond the frost line of another star, other molecules surfaced in the data, each adding to the puzzle. Cyanogen or CN appeared in small but persistent amounts. Carbonyl sulfide, a rare find even in the most exotic comets, showed up as well. Water, ice, and carbon monoxide were present, but in much lower quantities than expected. The usual suspects for green emission, like C3 and CN, were measured at levels far too low to account for the visual intensity seen in amateur and professional images alike. Chemists working with the raw spectra described the results as both exhilarating and frustrating. The green color was real, confirmed across independent instruments and careful calibrations, but none of the known gas phase radicals could explain its brightness. The data ruled out contamination from Earth's atmosphere, camera artifacts, or lunar eclipse effects. Every lab group that ran the numbers arrived at the same conclusion. 30 Atlas's coma is dominated by carbon dioxide with a supporting cast of cyanogen, carbonyl sulfide, and a handful of trace volatiles. The molecular ratios, especially the overwhelming carbon dioxide, set this interstellar comet apart from anything in the solar system. The chemical evidence pointed to a birthplace shaped by alien conditions, an environment where water was scarce and carbon chemistry ruled. For the first time, astronomers were forced to consider that the green glow might be coming from a molecule no one had ever seen in a comet before, or a process that operates only in the cold ancient outskirts of another star's planetary system. Spectrographs trained on 3Y Atlas revealed a pattern that left even seasoned comet researchers unsettled. Across dozens of observations, the usual iron lines so prominent in solar system comets were missing. Instead, the spectra glowed with the unmistakable fingerprints of atomic nickel. 22 distinct nickel emission lines, especially strong in the ultraviolet, stood out against a background almost completely devoid of iron. The most intense of these at 3,524.5 angstroms measured nearly 2 orders of magnitude stronger than any corresponding iron feature. Careful calibration and repeated cross-checks ruled out error. The comet's gas was not just nickel-rich, it was iron-poor to a degree never seen before. This anomaly sent theorists and modelers back to the drawing board. In our solar system, iron and nickel typically travel together, locked in the same mineral grains and ice, released by solar heating or photons. But in 3 Ice Atlas the balance was broken. Some speculated that the nickel originated from volatile organometallic compounds, molecules where nickel is bound to complex carbon structures, able to sublimate at lower temperatures than metallic iron. Laboratory analog suggests that under intense ultraviolet light, these nickel complexes could break free from the surface of fine dust grains, leaving iron behind in more refractory, heat-resistant minerals. The idea is controversial, but the data forced the conversation. To understand how such a composition could arise, cosmochemists turned to models of protoplanetary disks around other stars. In the cold, distant reaches beyond the carbon dioxide frost line, temperatures drop low enough for exotic ices and unusual metal complexes to form and survive. If 3I Atlas condensed in such an environment, far from the warmth of its parent star, it could have trapped nickel in volatile forms while iron remained locked away. Over billions of years, possibly more than 7 billion older than the Sun itself, these grains drifted through interstellar space, preserving a record of their alien birthplace, the Mfifa, nickel-dominant signature combi coma. Combined with the overwhelming presence of carbon dioxide, paints a picture of a world shaped by chemistry unfamiliar to Earth. For the metal line, specialists and theoretical modelers now poring over the data. 3 Atlas is more than a curiosity. It is a sample from a time and place where the rules of planetary formation played out differently, and where the ingredients for planets and comets could take on forms never seen in our own solar system. As October approaches, the world's most powerful observatories find themselves sidelined. Hubble and the James Webb Space Telescope, both designed to probe the deepest mysteries of the cosmos, are now constrained by their own safety protocols. Neither can risk pointing too close to the Sun, especially not during 3I Atlas's critical passage near perihelion, set for October 29, 2020. Music. The exclusion zones are non-negotiable. One misstep could mean permanent damage. Internal debates sweep through telescope allocation committees. Some astronomers argue for an exception, calling this a once-in-a-generation opportunity. Others refuse to gamble with irreplaceable hardware. In the end, caution prevails. The flagship eyes of Earth must look away. Yet while the debate rages on the ground, a solution is already orbiting another planet. Mars, trailing just inside the comet's path, offers a unique vantage point. Its fleet of orbiters, including the Mars Reconnaissance Orbiter and Maven, are poised to fill the observational gap. Mission teams scramble to retask instruments, securing precious target of opportunity slots for early October. On October 3, 2025, as 3I Atlas sweeps closest to Mars, these spacecraft will be the only platforms with a clear line of sight. Engineers adjust schedules, recalibrate detectors, and coordinate data pipelines, knowing that for a few days, Mars will become humanity's outpost for interstellar science. The gamble shifts from Earth's flagship telescopes to the ingenuity of planetary mission teams, determined to capture whatever secrets the comet reveals while the window is open. July 17, 2024, a team at the William Herschel Telescope in the Canary Islands captured something no one had ever seen in a comet. A polarimetric signal so extreme it shattered every previous record. The data showed the strongest negative polarization ever measured, plunging deeper than anything in the catalogs, not just for comets, but for any small icy body this close to the Sun. The team, led by researchers who had spent years chasing faint signals in the Kuiper Belt, initially suspected a calibration error, but repeated runs, careful checks with standard stars, and cross-validation with backup instruments all pointed to the same result. The phase angle curve looked nothing like those of solar system comets. Instead, it echoed the behavior of distant trans-Neptunian objects, icy relics from the edge of our own system, untouched for billions of years. This polarization pattern is more than a technical oddity. It speaks to the very dust grains swirling in the coma, hinting at a structure and composition shaped in an environment alien to anything the solar system has produced. At the same time, Hubble's sharpest pre-exclusion images set an upper limit on the nucleus, less than 5.2 kilometers across, possibly much smaller. The nucleus remains hidden behind a thick carbon dioxide-rich coma, but its faint thermal glow suggests a compact, dense core. Together, these findings offer decisive physical evidence. 3 Atlas is not just a visitor. It is a survivor from another star, carrying with it the fingerprints of a world we may never see. In late 2023, TESS was focused on the right patch of sky, capturing a steady stream of images for its exoplanet survey. Hidden in those raw frames, 3 Atlas slipped by just a faint moving point, never flagged by the automated pipeline. It would take almost 2 years and a global scramble before anyone traced the comet's path back through those digital archives. The Vera Rubin Observatory, still in its engineering phase in May 2024, also captured the interstellar visitor. But with its science operations not yet underway, The data sat unexamined, the comet's presence masked by the sheer volume of test images. Only after the official discovery did researchers comb through old datasets and realize how close they had come. Internal memos from the Rubin team called it the near miss that ended the era of cometary luck. Astronomers who spent decades chasing cosmic surprises now find themselves relying on survey algorithms and real-time alerts. The mood at conferences is a mix of pride and nostalgia. Pride in the tools that finally make systematic discovery possible. Nostalgia for the fleeting thrill of stumbling across something wholly unexpected. The lesson from 3I Atlas is clear. The cosmos rarely gives second chances, but it rewards those who look back as carefully as they look forward. From now on, every new interstellar object will be hunted not just by chance, but by design. Astrochemists and cosmochemists now find themselves confronting a new standard for what is possible in planetary formation. The chemistry of 3I Atlas, so unlike anything in our solar system, points to a birthplace shaped by conditions older and colder than the Sun, its overwhelming carbon dioxide, rare nickel-rich grains, and the absence of familiar molecules like dicarbon force a re-evaluation of how planets and comets form in distant star systems. Models that once relied on solar system examples now expand to include the legacy of stars born more than 7 billion years ago. Researchers compare this comet's fingerprint to the diversity seen in exoplanet atmospheres, searching for patterns that might explain the building blocks of worlds across the galaxy. Each anomaly in 3I Atlas becomes a clue, suggesting that the ingredients for planets can be far more varied and far more ancient than anyone had imagined. Survey teams are already preparing for the next cosmic arrival. The era of chance discoveries is giving way to a new strategy, systematic all-sky searches, designed to catch interstellar objects as soon as they enter the solar system. The Vera Rubin Observatory, set to begin full science operations in the late 2020s, will scan the sky every few nights with unprecedented depth and speed. Its automated algorithms, refined by lessons from 3I Atlas, are built to flag hyperbolic trajectories and odd color signatures in real time. Meanwhile, engineers and mission planners are sketching out rapid response probes, small spacecraft that could launch on short notice to intercept new interstellar visitors. Concepts include solar sail flyers, modular observation packages, and even swarm missions able to split and adapt as targets are found. This proactive approach promises not just earlier detection, but the chance to study these messengers up close, capturing the chemistry and structure of alien worlds before they slip away forever. On October 3rd, 2025, 3I Atlas will pass closest to Mars, just weeks before its perihelion, near the Sun on October 29th. Detailed analysis confirms this is only the third interstellar object ever observed in our solar system with a hyperbolic entry speed of about 61 km/s. Its chemistry, dominated by carbon dioxide, strong cyanogen, and a rare nickel-to-iron ratio, differs from any known comet, supporting evidence it formed beyond our solar system's carbon dioxide frost line over 7 billion years ago. Despite record-breaking negative polarization measured in July 2024, the source of its green glow and precise nucleus size remain unresolved, partly due to observation gaps as Hubble and JWST enter exclusion zones. Mars-based orbiters are now critical for capturing data that Earth cannot. As future surveys expand, 3I Atlas stands as proof that interstellar visitors can reveal the diversity of planetary systems far older than our Sun. The search for answers continues, guided by each new arrival.